Bem-vindos ao último dia da primeira Open Tech Week da Blip. Welcome to the last day of Blip's first Open Tech Week. As part of a multinational multi-location group like Flutter, a lot of our work is in English, so that's how we will continue this event today. At Blip, we believe that the more we share, the more we learn and grow. This Open Tech Week has been an opportunity to give back to the tech community, sharing our challenges and best practices, and creating an open space for learning with each other. We've talked about sharing technology that works across our divisions and brands. We've shared how we approached building a new betting experience for Betfair with quality embedded right from the start. We've discussed hosting and automation and some of the unique challenges we have to operate our platforms globally. And we've shared more about the challenges we have had to help our brands manage the prices and risk on their websites. You can play back all our previous sessions here in our LinkedIn event and reach out to us or our speakers directly. Today, we'll demonstrate how when you really understand your technology inner works, you can make the most of it. Each of our speakers will be able to answer any questions from you on the comment section of this stream, so please leave your questions and comments, and they'll be commenting back right after their talk. We'll start by hearing from Eduardo Pinto, backend developer on our sportsbook platform Strive. As a backend developer on sportsbook platforms, Eduardo has worked in different parts of our platform, which service almost all brands of the group. Recently, a project involved the addition of a search capability to the Paddy Power Sportsbook, something that is now being reused for other products, such as the new Betfair experience. In his talk, I'm feeling lucky building a search engine with Elasticsearch. He will go through the different challenges faced and give you some ideas on how Elasticsearch works and how to take advantage of such technology. Welcome, Eduardo.
Thanks, Mariana. Thanks for the very kind introduction. Hello, everyone. I'm Eduardo Pinto, and I work as a backend developer in Blip. So let me start by saying you that before I joined Blip, I had been a customer of Betfair back in the old days before the market got regulated in Portugal. So I was already a bit into this world of sports betting, but I was completely clueless on the scale of the business. So if you're a fan of the sports, like me, I have a question for you. Ready? So can you estimate how many professional sporting events are happening right now? So maybe a few hundred, low thousands? What I can tell you is on our sportsbook platform right now, we are offering around 250 events at this moment. So if you have to guess not only the ones that are going on right now, but the ones that are going on in, say, the next 2 weeks, what would be your guess? So what I can tell you is that, although I cannot give you a definitive answer, basically on Saturday afternoon, which is our busiest hour, we offer around 4,000 events. So across 40 different sports, from cycling to football, from darts to golf, across 500 different competitions, from Malaysian ones to Argentinian ones, all around the globe. And as I said, around 4,000 different events, which make up to 200,000 markets. So if you don't actually know what a market is, let's take a look at an example. So if you have a look at this Malaysian Premier League competition, we have this event from football, in which we have a team called Kuching and Terengganu. Pretty sure I mispronounced that, but that's fine. And for this specific event, we have different markets, right? Really a lot of markets. So some examples that we might have is who is going to win, what will be the final score, how many goals in the first half, or who will score the first goal. Now, imagine that I'm a football fan from Ecuador, maybe, and I really have interest in finding all the matches from my local team, right? And to know when they will play and how can I make a bet. So before we had this search functionality, it was very difficult for such a fan to find a very specific local team, because usually the top leagues appear on the front page, but not the other ones, right? So you had to go through several menus before you could get there. Now that we have this search available, every fan of Chacaritas from Ecuador, for instance, can really quickly find their events from their local team and to easily place their bets. And also, another example would be a cycling fan looking for the next competitions to try to guess the winner of those. So after I've got you on board on how important search is for improving our users' experience, I will start to talk about how we built this, right? So, and I usually like to break this down into two different pair of flows. So the first thing is, if you're doing a search engine, you obviously need some data, right? There's something you need to search on. And usually that data, those documents are somewhere, maybe in the database, maybe in a search engine, somewhere. And you actually need to make sure that on one end, that data is up to date, right? So you need to have some kind of business flow that makes sure that information is always up to date. And on the other end, you always need to have something, an engine that will be able to search the data, search that repository of information, and retrieve that to the users, right? So on our specific context, when we were implementing this search functionality for our sportsbook, we, on the right side, on the collecting flow, we had very specific constraints and requirements. So one specific constraint, or actually one specific characteristic, was that although there are a lot of events and markets, the data size is not that big. So the data size amounted to 50 megabytes. The other interesting point is that our documents, our information is very high volatile and short-lived documents. So imagine if we compare this use case with a use case of Amazon, for instance. When you're searching for a catalog for a product on Amazon, that product might be on Amazon website for several months, a year, or several years. On the other end, on our use case, our events are probably on site for maybe 2 weeks or 3 weeks. Obviously, there are some exceptions, but most of the events that you can find at a specific moment are only there and available for a few weeks. And so the third characteristic was that the way we collected this information, or the original source of the data, only provided us snapshots. That is, that for a specific point in time, we only had the full catalog of information. Now, on the other side, the side in which we try to find the documents that we are looking for, there were also some characteristics. So the search we were trying to build is what I would call an open search. That means that whenever the user inserts a term, we don't actually know if he's searching for an event, a competition, a player name. It can be anything, really. So, and this has different challenges than to build more of a structured search in which you know exactly what the user is looking for. Now, the other thing is also that we have some business knowledge. So we want to be able to somehow customize the way that the results are sorted, because we know that some sports are more relevant than others, for example. And obviously, the last point is that we wanted to be sure that this solution, these services, would be able to cope with high load of users, high demand of users, and also that we make sure that they are available 24/7 as our business requires it, right? So I guess one of the first decisions that we had to make was what technology to use as a repository for the data and as a search engine. And you're probably not surprised to hear that we've chosen Elasticsearch. So why did we choose Elasticsearch exactly? So we tend to use open source technologies in Blip, and there was really two options on the table, Solar or Elasticsearch. Elasticsearch is a bit more traction in the industry at the moment. And there's also another point, which is it was built with scalability in mind. And when we had the fact that were already using Elasticsearch for a different purpose on the company, we ended up choosing Elasticsearch. So what I will explain you now is a bit how Elasticsearch works for our use case. So Elasticsearch is a distributed document store, and in Elasticsearch, every document needs to be a JSON object. Okay, so, and more than being a JSON object, each of these JSON objects needs to belong to an index. Okay, so in this example, we have an index we called events, and we have some documents. Okay, so you can think of an index as a table on a relational database. Okay, it's pretty much the same. So what happens when we have too many documents to handle on a single node is that we can make use of sharding in Elasticsearch to make sure we handle those that many documents correctly. So if we create these index events with 3 shards, what will happen is that the 6 documents will be distributed across the 3 different nodes that we have, and we'll make sure that we have capacity to handle these documents and the load required. Now, another interesting feature that Elasticsearch offers us is to have replication. So in this example, if we look at index events with replication factor 1, what you see is that now we have a copy of the data for each shard on a different node. So if we look at, for instance, the blue shard, we see that maybe this is the primary shard, and we'll have a copy of the data on node 3. For the red shard, we have the same in 2 nodes, and for the green shard, exactly the same. So we always have at least 2 copies of the data. Now, so what happens when we receive a query from the user? So let's take a look at this example. We have someone looking for Manchester. Our engine will send this query to Elasticsearch and tells node 1, look, find me all the documents that match Manchester. And obviously node 1 only knows about a specific partition of the data, right? He knows about the events on the blue shard and the ones on the red shard, but it doesn't know about the ones on the green shard. So what it does is searches on the shards that he knows about, trying to find the documents, but will also send a request to node 3, which holds the green shard, and tell him, look, find me all the documents that match this query. And that node 3 will reply back with the results, and then node 1 will reply back to the user, to the query engine, then to the user. So this obviously requires a request to another node and an increased latency in our flow. So what we did actually for our specific use case was to take advantage of the fact that our data size is actually small. So although we have many documents, it's not a huge amount. So what we did was we configured an index with only 1 shard and 2 replicas. So what that means is that basically every node is able to serve any request, because when someone is searching for Lakers and that request comes to node 2, for instance, node 2 has all the catalog available. So it will be able to respond to any query without needing to coordinate with other nodes. And so that will be obviously faster. And we still also obviously have high availability, and we are able to cope with failures from one of these nodes because data is in the remaining ones. So after we saw a little bit how Elasticsearch works internally and how it guarantees the capability to scale and the high availability of our services, it's interesting also to understand how to try to make the most relevant results appear first, right? So let's look at this two examples. So we have a user searching for Benfica, and if you see on both sides, the first three results are actually the same, right? But on the fourth and the fifth result, on the left side, you can see that we are returning a result for esports, for FIFA. And although on the right side, we are returning a UEFA Champions League competition page and a Portuguese Premier League. So which one do you think would be the best? I'd say that the right one is the best. And we know that because we know our customers, right? So it's much more usual for a customer to be interested in betting in UEFA Champions League because Benfica is playing on it, at least for now, than to want to place a bet on FIFA or esports, right? So this is an example of the type of customization that we did to our rankings. And how do we did that? So let's take a look at an example. If we have this simple document, we have title, Benfica versus Porto, an event from Portuguese Premier League with a date, and obviously the football sport. So Elasticsearch gives you basically two different options to kind of try to influence the way the results are sorted. So one are weights, and weights are attributed to a field. So you can say that a match on a field like title is more important than a match on a field like competition. This is something that you can do. And another thing that you can do is actually boost something based on a specific value of an attribute. So say that we want to say that any result for the sport football is more relevant than any result for any other sport, for instance. Okay, so what actually happens when the user is trying to search for Manchester is that query engine doesn't say exactly find Manchester in events. It will say something more like this, right? It will say find Manchester in events, but make sure that we boost high profile sports. Maybe we devalue some low profile sports like esports. We know that our customers are not very interested in them. We might favor full matches on title. So if a user searches for a term and that is an exact match on the title of the event, that might be a good result to show up first. And also value some of the events that are soon to start, for instance, based on the start date. So there's a lot of different things you can do with this kind of tuning of the results. So the third point that I wanted to talk about is we've seen how Elasticsearch works and scales. We've seen how we can tune the rankings. And the next question is kind of how to keep, or how do we keep the catalog up to date? So if you remember, I've told you before that our source of information doesn't give us small updates per catalog item. It's just that at one single point in time, we have the whole catalog. So the first thing that we did here was, once we receive this snapshot of data, we break it down into different chunks. And to do that, we are taking advantage of a bulk API from Elasticsearch that will be able to efficiently index a lot of documents at the same time. And another thing that we do is to take advantage of alias. And here, so when we're trying to index this new version of the catalog, we'll create a new index called, I don't know, events2, for instance, and we'll start sending the documents there, and we will wait a bit for the documents to replicate to the other nodes. And once the documents are replicated to all nodes, we basically switch the alias from events to point to events2. And now, from now on, every customer will, any customer and any customer query will end up on a node that is already with the catalog up to date. So just to wrap it up, some key takeaways that I wanted you to keep in mind. Elasticsearch is a very powerful search engine. I think it's very easy to start and go. The defaults are very nice, and it's really easy to use its REST API. It's very powerful. Also, try to be careful when trying to tuning results. So what can happen when you start tuning results is that some of the settings that you make for a field might actually work against another one that you set up for another field. So you might end up in a state in which you cannot really explain how the rankings are being calculated, or you will, but you will have to dig up a little bit. And the last point I wanted to highlight is actually that I really think that understanding the internal basics of Elasticsearch will help you make a better use of it. And I guess that's probably true for any technology, as we'll also see in António's talk for sure, who is coming next. So the last thing I wanted to show you to prove to you that Elasticsearch is a very powerful search engine is that this curious graphic. So when we went live, it shows the capacity that we estimated and what was exactly the reality of the capacity that we needed. So this is just to show you how powerful Elasticsearch is actually, and how efficient it is. So if you're curious for more information, or to read more, or to watch more about Elasticsearch, be sure to check out these two talks. One by Shane Bavenen, which is actually the creator of Elasticsearch, and they are the two very interesting talks. Or the other option, you can also join Blip, and I guess I heard there's a few Elasticsearch trainings ongoing as well, so I'm pretty sure you will enjoy that. Thank you very much.
Thank you, Eduardo. Eduardo will now be answering your questions in the comment section of this stream. And we'll now hear from António Ramadas, also backend developer, but from our American division. As a backend developer, António and his team enable our American customers to follow and cash out their bets. At Blip, we want to ensure the most efficient usage of our web applications. Whenever our JVM applications run, a garbage collector runs in the background to release unused memory resources. G1 is one of the most common algorithms, and in his talk, Understanding G1 Garbage Collector, António will explain this algorithm while sharing some tips. Welcome, António.
Okay, sorry, remote presentations. Okay, so hello everyone. Thank you for the introduction, Mariana. My name is António Ramadas. I'm a backend developer here. I'm a backend engineer here at Blip. I mainly work with the FanDuel brand as operates in the United States, and I mainly work with the sportsbook. If you want to know more about sportsbook betting, please check Tuesday's presentation where we dive deeper into what is betting on sportsbook. Throughout the presentation and even after it, feel free to drop me an email or drop a comment on the comment section. If you're like me, and thanks to the Eduardo presentation on Elasticsearch, we saw how powerful it really is. And one way, if you're like me again, you will want to experiment it. And one way to do that is by developing an application to interact with it. So we may start by creating simple methods like this one, where in this method, we create two objects. By the end of this method, and these two objects do stuff. By the end of this method, once this is called, and once it returns, these two objects are no longer reachable. So they may be collected in memory. We can save memory by reclaiming them. So one definition is that they are garbage illegible. And if you want to see how that happens in the background, because JVM takes care of that from us, is that we can see that there's a heap usage and also non-heap usage. So JVM splits the memory into two, heap and non-heap. Whenever we allocate new objects, they mainly go to the heap area. And if we look into further how heap is built, we'll see that it's GVM actually, and G1 in fact separates into main regions: old gen and new gen. We may also call this new gen young gen, and we may call it from onwards. We also have two main GCs. So we have two main regions, and we have two separate algorithms that act on them. Whenever we create an object, they will go to the new gen. And it is frequent for the GC to run periodically. That's okay, because the goal is to be fast. But still, spikes may happen. And it's good to know what is the cause from it. And one way to do that is by understanding G1. And this is what we will understand today. We'll be able to look at the logs that G1 prints, and we'll be able to at least know or pinpoint or guess where the problem might be. And we see that it is somewhat complex. There are a lot of stuff going around. But the goal today is to be able for you to understand it and at least know where to look up, what values should not be as they are, and act onto them. It's worth mentioning that we're talking about garbage collectioning, and in garbage collection, we have several algorithms. We have serial, parallel, CMS, for instance, but today we'll talk about G1. That sounds really cool if you try to say it, G1. G1 stands for garbage first. But before really understanding it, before we understand how it runs, we need to understand the heap layout. So G1 is sparked and divides the heap into multiple regions. Here we can see we can see that it separates into multiple regions, and the region might be Eden, Survivor, Old, or Among Us. It is important to know that once we will locate an object, it will go to the Eden region. In total, there should be about 2048 regions, and each region will have a power of 2 to ease lookups. Each region, so whenever we allocate an object, that object will go to one of these regions. And so that means that one region has at least one object, except for the Among Us region, which is special. And once an object is allocated to this region, we may call it an Among Us object. Among Us objects have a special property. If they are at least half the size of the square of this region, then this region will only contain the object itself. If the object outsizes the size of the square of this region, then it will occupy continuous regions. So if you're trying to allocate a really big array, it's possible that it will occupy multiple regions. In general, you should aim to avoid those, but it's okay if it happens. Here, we can also see that we have some regions that are empty. Those are okay. We can call it empty regions. It's also important to know that Eden and Survivor are called young, both together are called the young regions. And we also have the old region, that's mainly about old regions. In general, G1 is really powerful, and it tries to self-tune itself. In general, with G1, you give it a target. So you say, okay, I want you to run in 200 milliseconds. That's the default. If the execution goes above that, then G1 will try to reduce the size of the young region. Otherwise, if it is below that mark, below that target that we gave it, then it knows, okay, I can grow, so I don't have to run as frequently. But we will see later on how that adds up. And now we're ready to understand the object lifecycle, which I already gave a few spoilers. Once you allocate an object, it might go to the Among Us regions and stay there, or it will be allocated to the Eden regions. And it stays there until we run again, so G1 runs periodically. And once we run it, the object will go to the Survivor regions. And it stays there for a while. And if it lives long enough, it will go to the old regions and stays there for a while. It's important to know the object lifecycle. So be able, once you look at the logs, you at least know what is going on. And also when you see different GC, so young GC that acts on the young regions, and also on the old GC that acts on the old regions, you'll be able to know what is going on. You may also see that there's a tenuring age. Each time G1 runs, it increments a generation counter by 1. So you run one time, the counter is 1. We run twice, 2, and so on. After an object lives for a few executions, it is considered old. It tenures, and it tenures to the old region. Whenever that object is no longer accessible, that object is considered dead. So we can remove it from memory. We can forget it. In the previous example that we've seen, we located 2 objects. Those objects came to Eden and probably didn't make it to the survivor, and it ended up right away on the garbage, possible to be garbage collected. Now, bearing this in mind, we can now discuss about young GCs. There are 2, old GC and young GC. We'll start with the younger one. So there's the memory layout that we've seen before, the heap layout actually. And young GC acts on the Eden region, mainly on the Eden regions, the survivor regions. Once that happens, G1 will try to compact memory, similar to Tetris, to be more efficient, to compact. So G1 really plays Tetris in this stage. We can see that we are moving these 3 squares or regions, Eden and survivor, together. That's because, and remember the life cycle that we discussed before, that an object moves from Eden to survivor, so we can move things together. So you may see that objects go from one place to another. Only live objects are copied. So more copies there are, the longer it will take. And so it's worth bearing this in mind, because there are a lot of garbage collectors, and you should know what is really best for your use case. But you may wonder, okay, so I'm moving things around, I'm shuffling, I'm compacting memory, but what happens to the pointers? So let's say that I have an array here, then I just allocate a new element, and I'm moving things around. How does G1 keep track of it? Let's look at a more concrete example. Let's say we have an object A that contains an array C, whose second element, or really the first one, if you start counting by 0, contains the D object that we just created. Whenever that happens, once you have an array and you're trying to allocate this object, so you do new D, and now you're trying to allocate to the second position. That object, G1, has a different data structure that is called card table. This card table splits the heap layout, the heap memory into separate ranges. And we may consider a card table a bitmap. So this single bit, actually it's a byte, but let's call it a bitmap. So a bit means that we're looking at this range. And that just means, okay, at this object C, at this region, we're updating this, we're making an update, an inter-region pointer. And G1 just does that. And the background just creates a dirty value. However, in the background, and your application continues to run, in the background, there's a thread or a group of threads that will go through these updates and will update the remember set. The remember set is another data structure. While a card table is a common data structure to all the heap, remember set there's a remember set for each region. The remember set basically says this. Okay, so I'm on this square, on this Eden region, and I have a pointer. Someone is pointing here from another region, and it points to this area. If we didn't do that, once we do a young EC, and the young EC acts on the young region and the all survivor regions, that we'll just say, okay, we don't have any pointer to D. Nobody is pointing to D. That means that we can drop it from memory. We can clean it. We can reclaim that memory space. However, with the member set, we don't need to traverse the whole old regions. We just need to know this specific area. If C is alive, then D is still also alive. And this is important because a young EC, and this is why you may see all the phases red, that's because that's a stop of the world. Once a young EC is running, your application is not running. And you may be panicking by now because you wonder, okay, my application is fast. Yeah, but G1 aims to be run frequently, but being fast. And that's a trade-off on the garbage collectors concept. There's a trade-off between latency and throughput. G1 values more latency, so there will be more frequent pauses, but short ones. The other side would be more not so frequent executions, but a longer time to run. We'll see later on that the industry has made major steps into making this more efficient. But for now, we can see that there are 6 phases, mainly 6 phases. First, we need to know what regions should we collect. So a young EC acts on the hidden and survival regions. Let's save those. Then we need to know the routes. Imagine like we're traversing a tree. We need to know where to start. And that's this phase. We want to know, for instance, static variables, the thread stacks, and so on. Then, and because you remember, the remember set is updated in the background asynchronously. So we need to stop all the ones. Now that the application is stopped, no updates are being made, but we need to process those. So we have a really up-to-date remember set. And once we do that, we'll be able to traverse the tree and have an updated view. And that's this step. And now we traverse the tree, we know what objects are alive because that's the ones that we touched. The others that we didn't do anything, that we didn't reach to them because they are unreachable, those objects are considered dead. And only the alive ones are copied around. Once that's finished, there's reference process where we process weak references, soft references, and so on. And that's mainly it for the young EC. And that will lead us to the old EC. Whereas the young EC was a full stop of the world, the old EC is a bit smarter here. First, it piggybacks on the young EC. Okay, give me the places that I should start looking up. For instance, you can create an object and point to an old existing array. Okay, and that's what it does at this step. Afterwards, and because the old EC acts on so many old regions, there can be lots of them, and this may take a while. So you don't have to stop your application the whole time. G1 will traverse this tree while your application is running. So your application is not running at the full potential, but is not stopped for a lot of time. That's also why G1 starts a bit early running on the old EC. There are a lot of parameters going around. Everything I talked and I will discuss, you may assume that G1 is very configurable and there's a way for you to configure it. Generally, a couple of parameters and you're good to go. But this is important once you face more specific problems or very specific use cases. So you should bear those in mind. Afterwards, and now that we've traversed this tree that goes from pointer to pointer, and your application is also running, so your application is also making updates to the pointers, well, now G1 will say, okay, due to possible race conditions, I may have lost a few updates. Let me stop the application and process those. And I will process those missing updates. And now I have a complete view of what objects are alive and what not. Very likely, you'll have old regions that are full of garbage. Those could be collected, reclaimed right away. You don't need to do anything. Whereas if a region has both dead objects and the live objects, then you need to copy things around to compact memory. G1 likes to play Tetris. And so G1 is here also smart. It will say, okay, I've taken a longer time to process the old GC. Next time, young GC that you run, process a few of these old regions, 1/8, that's the default, 1/8 of the old regions that I know that they are good to go, to be cleaned. So when the next time the young GC runs, it will mainly run young region, hidden regions, survivor regions, and a few old regions. So at this point, let's do a very quick recap. There are two main regions, young and old. Young as hidden and survivor. And there are also two main phases that act on the respective main region. That's a young GC and an old GC. And you mentioned, if you notice that I mentioned object copy, so live objects being copied around. So the more live objects there are, the longer the G1 will take. And you also see a bunch of red stuff there is. Not that is wrong, but that means that there's a stop of the world. And that's okay, because the goal of G1 is to be be fast processing those objects. So fast execution, but a frequent one. So you may see very frequent counts, very frequent executions. If you go to the previous slides, you'll see on our dashboard very frequent runs. That's okay. In general, G1 is very easy to tune, and you can just give itself a target. However, if you give to a really low target, that means that G1 will have to collect fewer regions. If it has to collect fewer regions, and because your application keeps allocating new objects, though that young region will be full faster, and that means more frequent GCs. Whereas if you give a very relaxed target, the young region can grow, can expand, and you'll have not so frequent executions. Besides, I know that I've discussed the young GC, old GC, but if you face this in production, you may eventually see a full GC. No, it's not that good. That means that either an allocation failure, so your application is working faster than G1, or you have a two-space exhaustion. That means that there's no enough space to move things around. From our experience, there's three main ideas here. First, you can either increase the heap size. Second, perhaps relax the target, give more room for G1 to run, or you can try to anticipate some of the work. We give here a few parameters. Feel free to pause the video later on and to read them through. As a good rule of thumb, you mainly need 3 parameters. Well, the first 3, everything is important to know, and you should be aware of your use case. But here we recommend you define the target. That's the target that G1, remember when I mentioned, so the size of the young regions can either grow or shrink according to the target. That's the target. It is a soft target. The default is 200 milliseconds. G1 will try to run it in 200 milliseconds, but that might not happen. And you also should tune the size of the heap. And there's also another interesting property that is not so well known. Whenever G1 runs, you can say, okay, so you run your process, but give my application some milliseconds. So you can configure G1, okay, run, give me this time for the application to run. Run again, application time, and so on. But you should not if you put here 1 day, that doesn't mean G1 will not run for a day. Again, G1 will self-tune and help you, but it's up to you to provide realistic values. And finally, we strongly recommend that you enable logging and you monitor your application. Otherwise, you possibly wouldn't know that problems are happening, or if they happen, you probably don't know the cause or how to act upon them. I've talked a lot about G1. I mentioned serial, CMS, parallel. Those are all garbage collectors, but there are also a few others. There's Shenandoah, ZEC, Epsilon. Epsilon is a no operation garbage collector. It does not clean the memory. It may be very fun to play with, or either to develop for very specific use cases. Whereas Shenandoah and ZEC are very promising. They aim to run in sub-milliseconds latency. So you should, if you notice, G1, that's the default, 200 milliseconds, either ZEC and Shenandoah, actually both of them, will run much faster. There's a few trade-offs, remember, latency over throughput, but still very promising. However, G1 is not dead. It's here to stick around. And there are a few references that helped us out, and we are sharing with you. I strongly recommend that you check the first reference. That's a video from Simone Bordet. That's really great. Also, we include a few references for log if you want to understand better how to interpret the G1 logging, and also to fine-tune it. As always, you can drop me an email or drop a comment on the section below or on the side. Thank you.
Thank you, António. António will now be answering your questions in the comments section of his stream, as he mentioned, and we'll allow for a couple of minutes for both Eduardo and António to interact with you in the comment section, and then we'll close this session one last time. Thank you for joining us for the last day of our Open Tech Week. Feel free to browse our website for more information on Blip and the Flutter group, and reach out to our speakers or to us directly here on LinkedIn if you want to discuss things further. We hope you have enjoyed these 10 sharing sessions, and we'd love to hear from you on what you enjoyed the most and what other topics you'd like us to cover in future sessions. Obrigada pela companhia esta semana.